if this solar or sun, these kind of things is not going to work, how can we make it a better world in sense of clean and without pollution, without things, a clean and better world? And the question is that, can the world run on renewable energy? Yes. The answer is yes, but it is not an easy task. So my main intention of today's talk is to take you from the clean energy, from the very basics of the very fundamental or the basic of the materials, that is atoms. So the basic constituent of the matter, the atoms, to the clean energy technologies. So this is my my prime intention of today's talk. So the outline I can say like this. Incidentally, there is an atom. So I just put it as a Jeep atom. Since it's my favorite vehicle, I put it as a Jeep atom. It could be anything. So I want to take that atom from that particular position to the clean energy technologies. You can see the left corner of the screen, the clean energy technologies. But this is not a straight path. You can see there are many ups and downs. So it is not an easy task from the very fundamental or constituent atoms to reach from the atoms to a clean energy technology is not at all an easy path. A lot of difficulties are there. We need to cross different hurdles. So what and all those things, we need to look into that, or we need to take a swab to look into some of the other things. So that is the outline of my talk. So we need to have a look into electrons and quantum mechanics. So all the engineering students and all the physicists or the chemistry background students all learn the quantum mechanics in their first year classes. And I will briefly explain how can we use the quantum mechanics for today's talk, and a very brief introduction of density functional theory. So that is one of the most sophisticated computational approaches what we use for the materials modeling. And we use the materials, some of the materials and its properties related to the clean energy technologies. And I will explain how we use the density functional theory for the clean energy technologies. And at the last, I will discuss how we can correlate the past, present, and future of the battery technologies. Okay, so I told you that I have a couple of puzzles for you. So I told you the atoms, the very fundamental or the fundamental constituent of matter. So I have a puzzle for you. So I have 4 questions over here, not question, 4 statements. So among the 4, one statement is wrong. So you need to spot that wrong statements, or you need to spot the lie. So the statements are, the atoms are indivisible pieces of matter. The second one, there are more atoms in a grain of sand than there are people on Earth. And the third one, atoms comprise less than 10% of the total mass energy in the observable universe. And the fourth one, electron microscope allows us to see atoms. Among the 4, one statement is a wrong statement. So can you spot the lie? I request you to unmute the mic and please say the answer. So let's make it more interactive. Any comments? Any comments? Any comments? Nobody? No comments? Just unmute your mic and just say the answer. Just a wild guess. Let's make it more interactive to move further. No answer? Hello?
Sir, is it number 4?
Okay, number 4. Any other option? Any other option?
Second one.
Okay, good. Any other option? Any other option?
Third one.
Third one. Okay, one more option. Nobody? Okay. So the first one was the atoms are indivisible pieces of matter, and we will discuss about this later. The second one is that the statement is a true statement. There are more atoms in a grain of sand than there are people on Earth. We have only, you can see there are around 10 to the power 19, that much big number of atoms are present in a grain of sand versus around 7.4 billion, around 740 crores people on Earth. And atoms comprise less than 10% of the total mass energy in the observable universe. Yes, that's a true statement. The rest is dark matter and dark energy. And the third one is electron microscope allows to see atoms. Yes, that is true. And the right side, you can see this is the arrangement of atoms in one of the materials which was reported in the Oregon, United States, Oregon National Laboratory. So the wrong statement is the first statement. So atoms are not indivisible pieces of matter. They are divisible pieces of matter. And we are well-known things like the nucleus. An atom consists of nucleus, the 99.997% of the total mass, and it has the protons and neutrons, and the electrons. It is a negatively charged particles, and which gives us everything, the electrons, which gives us everything, the colors, the smells, the odor, everything. So the electrons actually makes our life or more easier, or which gives a meaning to everything. So we need to look into the electrons. So we actually started from atoms, and now we know that atoms are divisible pieces of matter, and it has the proton, electrons, and neutrons, and the electron has a major role for most of the applications. And now we are going to look into electrons. But when we want to deal with electrons, we need to have a look into quantum mechanics. I'm not included any complicated equations or anything. It's very fundamental things, and I will try to make it very fundamental to understand to each and everyone. So let's have a look into the electrons and quantum mechanics and Schrodinger equation. So this is the fundamental equation in the quantum mechanics, like F is equal to ma in the classical mechanics. So remember that this is the very fundamental equation, so you cannot derive this equation, but you can deduce these equations from the wave equation and all. So that is more mathematical thing. So the question is whether these electrons obey Schrodinger equation, and this one equation is suffice to rule all those electrons. Yes, the answer is yes. So if we look into these things, it's all about probabilities. I told you the electrons which revolve around the atoms. Okay, so it is in the revolving fashion. So it's all probability. So the probability of finding an electron, that is the base concept. So there we have a Schrodinger equation, and you see, so this is the Planck's constant, and the other one is the mass of electron, and this is the potential felt by the electron, and this is called the wave function. So this is nothing but the probability of finding an electron in the system. So the probability of finding an electron in the system, and this is the conventional, the energy of the system. But okay, we have a Schrodinger equation, and we assume that this equation, we can use this equation to find out the probability of an electron, which can be used to solve the many of the underlying physics or chemistry. But there is a problem. Although we can use this equation to solve the most of the physics and chemistry of the system, but this is very complicated. This equation is very complicated. That means it's very complicated to solve a system with a large number of electrons. If you see if a system with 10 or 20 or 30 electrons, it's very difficult to solve this equation analytically. So we need to have some numerical methods to solve, even though it is very difficult. So there comes a problem of data. Data means it includes everything. You have credit card information, debit card information, your Instagram, Facebook, Twitter, all those email, all those accounts. So we need so much of data. So we have a data storage center like that. In order to solve the things using computationally, we need to have a proper data storage facility. Okay, so this picture is the Texas Advanced Computer Center of the United States National Science Foundation's facility. And I use this system to store my data or my computational data. Okay, the problem is that, for example, I told you the wave function. So in order to store the wave function of one silicon atom, which contains 14 electrons, you need 10 to the power 30 bytes of data. And it is something very huge. I don't know how to pronounce that number. But the world's total data storage capacity, including our cell phones capacity, our hard disk, pen drives, and all the things, it comes around 10 to the power 22 bytes. Then how it is possible to store such a huge data in? It is not possible to store. Then what is the solution? Yeah, there are some smart people, and they found that electrons are identical. So consider these are a set of electrons. So you can see my mouse. So these are electrons. Assume that these are a set of electrons, and I told you the probability of finding all these electrons are represented as psi, the capital letter psi. But I told you the electrons are identical. Okay, then what we can do? We can replace that capital psi with a small psi. So this is what the ancestors, the great scientists, they did. Because of this identical nature, they replaced the capital psi with a small psi, and there comes the entry of density functional theory. And Professor Walter Kohn awarded the Nobel Prize in Chemistry in 1998 for his development of density functional theory. So it is very recently, hardly 20 years back. So you see how powerful it is. So have you seen this equation before? Yes, this is something like the Schrodinger equation. So here the things are same. So instead of that capital psi, here we treated this as a small psi. That is the wave function of one electron. So it is something like taking a census. In our this Google Meet, in this webinar, we have around 50-60 participants, and if all looks same and all our weight, height, and everything is same, then instead of taking the details of all individual people, we would prefer to take the data of only one person. So that is enough, because all actually resembles each other. The same thing in the case of electrons. We are not going to take the whole electron in the system, taking only one electron, and the rest is same. So how the potential felt by one electron by the other electrons, and how it is the interaction between the electrons and the nuclei, and other one is the Planck's constant and mass. So this is the basic thing. Okay, so the problem solved. So here the basic thing is, the basic definition of a density functional theory is nothing but it is a method of obtaining an approximate solution to the Schrodinger equation of a many-body system. That many bodies are nothing but the many electron system. So you can see here we have 3 electrons are over here, and here we treat that the electrons are electron density or electron cloud, and we assume that as electron cloud, and we start from that electron cloud as a starting point. So this is the very fundamental thing. And here the density functional is that the energy is a functional of ground state density. That density is nothing but the electron density. So this is the very fundamental idea, and we use a bridge. So we have we have electrons, we have atoms, we have electrons. In order to solve electrons, we have quantum mechanics. So in order to solve the data issue or data storage issue, we have Schrodinger equation, and we have a tool, that the density functional theory. Then how to solve that things? So there comes a bridge. So the bridge is nothing but the computational approaches. So I would like to say that the role of the computational approach is not at all to replace experimental or theoretical approaches. Its role is to bridge the gap between theory and experiment, to support the theoretical and experimental aspects to to make the things more faster, more clear, and more efficient. So this is the fundamental idea of the computational approaches. It could be anything: computational physics, chemistry, biology, and other kind of engineering subjects as well, because nowadays everything is interdisciplinary. All right. So now we started from atoms, and we just had a quick visit into the electrons and quantum mechanics, and now we should go through the material properties. So how we can use the things to predict the material properties. Okay, so if I talk in terms of computationally, we have the materials modeling techniques. So what is a model and what is a simulation? So a model is the physical representation of a system or a real system. I showed you a Jeep. So that is actually a model. So that is a model. So when I use that system under certain set of conditions, so then we can use that as simulation approach. So the one is a mathematical or a physical representation of a system, and simulation is nothing but we are applying set of conditions to that system for the simulation purpose. So we have a different kind of material modeling techniques like ab initio, atomistic, continuum, and macro scale. And I am particularly interested in the ab initio as well as the atomistic methods, because those two areas are more related to the fundamental sciences, and we assume that they provide more high accuracy results, although they are computationally very intensive. And today I am discussing only the ab initio techniques. The ab initio means from the scratch, or we are actually dealing with the electronic level calculations. Okay, but the computation is it is not like an easy task. Most of you might be doing some coding for your project and thing. So the computation is something like what we give as input, it will give as an output. It's something called GIGO, garbage input, garbage output. So we have to have an insight always. We have to know what is actually we are doing. So we have to have a clear-cut idea what we are trying to simulate or what we are trying to model, and how we are trying to implement that for a real purpose application. Otherwise, it will be something like this. So you might have heard the story that the blind man asked to describe the elephant. So each person who touched its different parts of the different body parts of the element said that, okay, the person who touched its tail told that, oh, it's like a rope, and the one who touched the body of the element told that, oh, it looks like a big wall, and the one who touched its ear told that, oh, it's like a mat. So it is something like that. We should know what is actually we are trying to do, and how to do, and how efficiently, how effectively, without spoiling the science behind things. So that is very important. So the thing before you compute is always very important. Okay. Now, what are material properties? So we have a large number of material properties. So we are experiencing different material properties, right? If you are boiling a cup of water in a vessel full of water, and if it is a steel vessel, and if you touch that while heating, if you touch that vessel, you feel, right? So that is actually that material property. Why the material is having such a property, when it heats, that material showing that behavior. So there are different properties, like chemical properties are there, the physical properties are there. We have a large number of material properties, but all these material properties depends on two factors. The first one, what kind of atoms. We have a large number of atoms in the periodic table, and these atoms, whatever it is, if you are dealing in a resistor in your lab, or a microcontroller, or IC, or a capacitor, whatever it is, all these things are made up of some kind of atoms or materials. So what kind of atoms and how they are arranged, these two things are the fundamentals of the material modeling as well as the material related things. So we can have different class of materials, like we can have a zero-dimensional material, or we call it as a quantum dots, or we can have a one-dimensional rods, or we can call some as a two-dimensional material. That is one of the most vibrant fields in nowadays, and the bulk system which we generally deals with in our day-to-day life. All these things are depends on two things: what kind of atoms and how they are arranged. Okay, now I have another puzzle for you. Okay, I just want to know how much you are paying attention to this interactive session. Okay, so I have models of 3 materials. So this is a model. Okay, this is not a real thing, this is a model. So most of you might be knowing what all these things. So I have a couple of questions. So please unmute your mic and please tell me the answer of these questions. Okay, these are 3 models. So you may need a wild guess. Okay, just guess and say. Let's see what is actually happening. So which one is the highest density? So the density means the amount of stuff per unit volume. So which one is having the highest density among these 3 models? Any answer? Any answer? I'm sorry, I didn't listen. Any answer? Hello?
Please unmute your mic and answer the question, or write in the chat box.
Madam, if they write in the chat box, I couldn't see that because I make it as a full screen.
Okay,
So,
sir. Okay.
So please unmute the mic and tell me the answer.
First one.
First one. Okay. Any other answer?
Third one.
Okay, good. Any other option? One more person can try. Okay, so the answer is second one. Okay, so the second one is having the highest density. Okay, so I have another question related to the same material. Which one is the hardest? That means how much force you need to deform one of the materials. If I say a very simple example, I have 3 pots. One is the plastic one, other one is aluminum, another one is steel. And if I have a hammer and if I hit the three pots, the aluminum, the plastic one, and the steel one using the hammer, and which one will deform very fast?
Sir, third one.
Okay, third one. Okay. Any other option?
First one.
Okay. Any other option?
Plastic.
Second one.
Plastic.
Aluminum.
Plastic is good answer, but I am asking about these 3 models. Okay. Somebody told the second one, right? Yeah. Any other option?
Yes.
Okay. So the answer is it's second one, because the second one is the hardest one, because its volume change is very, very low as compared to other 2. Okay, and the last question related to this thing. So you can just a wild guess. So which conducts the electricity the best? Which one is the among the 3 is the best electrical conductor?
First
Third one.
one.
Okay, first one, third one. Any other options?
First one.
First one. Okay. Okay, so most of you are right. So the answer is the first one. So the first one is a conductor, the second one is an insulator, and the third one is a semiconductor. Okay, so do you know what all those things? The first one is nothing but the graphite, and the second one is the diamond, and the third one is a carbon-60 fullerene. It contains a 60 carbon atom. So what I want to convey from these three examples is that all these things are the constituent, or this contains only carbon atom. You see, all these three materials showing different properties, entirely different properties, and they are consist of only carbon atom. That is how these, what kind of atoms and how they are arranged. Okay, all the things contains carbon atom, but due to its different arrangement, we can have the hardest non-material, that is a diamond, and it shows other different properties. So this is, I just want to tell you through this puzzle. Then how can we use the density functional theory to solve these kind of issues, the fundamental? Suppose if I designed a new material, or if I design a new material, and how can I know that this material is showing these kind of properties? So there we use these computational approaches to get more insight on that particular property, especially the fundamental properties. So the first thing, what kind of atoms and how they are arranged, and we use the density functional theory calculation along with the Schrodinger equation and relevant physics and chemistry and other associated sciences, and we will get the information of whether it is transparent or bendy or rigid or hard or soft or conductive or insulator. So all this information we can obtain using the fundamental density functional theory analysis. Okay, now if you see, if you replace our calculation, that information with the diamond, we are supposed to get the information like it is a transparent, and it is a hard, and it conducts heat, and it does not conduct electricity. So this information we can obtain through these kind of computational approaches. Okay, so this is just I want to let you know. Okay, now we have to move to the design of clean energy materials. So we started from the atoms, and we just take a swap into like the electrons, quantum mechanics, and some of the materials properties and how they are arranged and what kind of atoms, kind of stuff. And now we want to take a look into the clean energy technologies. Okay, all right. So I told you we have a set of atoms and how they are arranged, and we are using a computational toolbox. I told you the density functional theory is one of the techniques. So we have different computational tools or techniques to model the materials, including the energy materials. But I use the density functional theory and molecular dynamics methods mostly for the design of battery materials. Okay, and we need to understand the clean energy materials, how we can use this. Okay. When I showed you different materials for different applications, but in order to design the materials for the clean energy technologies, we have to have some of the advanced materials. We can have different lightweight materials and functional materials and emerging materials, bio, nano materials for different applications. And I am particularly interested in the functional materials. And you can see the applications of functional materials. It is ranging from our steel tubes to our like the most sophisticated, most recent technology like medical field also we can use. And the right corner you can see the electronic materials, and all of the students like electronics and communication engineering students might have experience with these things like resistors, so capacitors and ICs and microcontrollers. So we are using some of the electronic materials for the design of that thing. And today I will talk about the energy materials, only energy materials. Okay. So how the electrochemical energy storage things are possible. So using energy materials, the batteries for clean energy. So we all are using batteries. Actually, we are carrying batteries in our mobile phones, in our laptop, and in our electrical appliances, home appliances, tools, and it has a lot of applications. So it is one of the most relevant power sources at present, and we can find its application everywhere, including electric vehicles. So the lithium-ion battery actually revolutionized the world. Because of that reason, this lithium-ion battery awarded the Nobel Prize in Chemistry in the last year. And these three professors, so they started before my birth in 85 or and in that time they actually started the battery research. The Professor Goodenough, Professor Whittingham, and Professor Akira Yoshino. The two of them are American scientists, and the Professor Akira is a Japanese scientist. And the Nobel Committee, they declared that these three persons actually created a rechargeable world. You can see in the figure, we can store the renewable energy in our battery, okay, and we can use that for almost all applications like transportation, telecommunication, and we are depending on those things for the lithium-ion battery. So this is one of the most powerful developments in this current era. So the lightweight and the rechargeable and powerful battery is now used in everything from mobile phones to laptops and electric vehicles. So it can also store significant amount of energy from solar and wind power, making possible a fossil fuel free society. So we need to make our environment more clean, and to accommodate each and every, not only the human beings, but animals. And we need a balancing environment to make a fossil fuel clean society. Now, let's have a look into the lithium-ion battery. Okay, so high capacity lithium-ion rechargeable batteries. So this is a very simple structure of a lithium-ion battery. In the left side, you can see a cathode. This is basically a lithium containing oxides like lithium cobalt oxide or lithium manganese oxide. And the right side, we have an anode material. In between, you can have a separator. Okay, the role of the separator is okay, so the separator actually what it does is that it actually blocks the contact between the two electrodes. Otherwise, it will come closer and the shortcut circuit will happen, and the system will break. And during that, and there is an electrolyte, usually the organic electrolytes, and this separator is a semi-permeable membrane. During charging, the lithium ions from these, the cathode material will move to the anode material, okay, and it will accumulate in the anode. So anode is generally a carbon containing system like a graphite. So you can see the layered structure. So during charging, the lithium will it will penetrate the semi-permeable membrane or the separator, and it will move to the anode, and it will store in the anode. Okay, during discharging, it will go back to the cathode. So it is in a shuttle, the lithium-ion shuttle between the cathode and anode. During charging, it will move from cathode to anode, and during discharging, it will move from anode to cathode. So this is the basic working of the rechargeable battery. And we can have a variety of materials. Actually, people are trying to make it as a more accurate or more feasible material to satisfy all our day-to-day needs. Okay, and my interest is basically hold on the anode materials. Okay, so I have a question. So what do you think? So I have three statements. So I told you lithium-ion battery. So why lithium is important? I didn't say like any other kind of metal, like any other kind of atoms in the periodic table. I told you the lithium-ion batteries. Then why lithium is so important? So is it because of the low density lithium floats on the liquid electrolyte? Or is it because of there is an energy difference for lithium between the electrodes? Or the positively charged lithium is attracted to the negatively charged electrolyte? So can you have a guess, any wild guess? Why lithium is so much important as compared to lots of atoms in the periodic table? Why lithium is very important? Any suggestion? No?
Participants, please unmute your mic and answer.
I'm just asking you. It's a kind of wild guess. Like you can just guess. Okay, so
Low density.
low density. Okay, any other option? Okay, so the answer is the second one. So actually lithium, which gives an energy difference between the electrodes. The electrodes is the anode and cathode. Okay, so you just assume the just look into that waterfall. So lithium, you know that it's a highly reactive metal. So maybe in our high school classes, we usually know that we used to keep this in some oil or some water because it is highly reactive metal and its charge density is very high. So what we do is that the lithium is a highly reactive metal, and here you can see that in the case of anode material, when lithium is associated with anode material, its energy is lesser than as compared to with the pure lithium metal. And when it associated with the cathode materials, its energy is again lower. So these energy differences between these when lithium is occupying different materials, and the energy differences of lithium associated with different materials gives everything for the electrochemical reaction. So this energy differences tells us the voltage of our battery. So if you look into your battery or mobile phone battery, you can see there's 3.7 volt or something they have written. So that is basically the average energy difference between the cathode and anode. So this is so the lithium is very important because of this high energy density. Okay, and if I talk about the charging and discharging, so this is the picture. You can see the Tesla's Roadster. This is the 2020 edition of Tesla's new Roadster, and they actually achieved at a single charge, it can go up to 620 miles. That is 1,000 kilometers it can go. So that is a great achievement as far as the electric vehicle field is concerned. Otherwise, because we always are facing an issue, the capacity issue that I will talk later. So what usually happens? So during discharging, the lithium from the anode will move to the cathode, and which actually during the discharging the vehicle is moving, and while charging the electrons will move from, or the lithium will move from cathode to anode. So this is the basic principle, and this is a great achievement as we concerned in case of Tesla Roadster. They are the world's largest electric vehicle automotive system. Okay. And if I speak to a very little about my research, there are two key concepts. One is the storage capacity. I told you the storage capacity. How much lithium we can store in the anode is a very important aspect, because what is our aim? If you fully charge your phone in the morning and you need to browse internet, you need to watch YouTube videos, and you need to Facebook, WhatsApp, Instagram, and all social networks, and you need to make calls, and you need to watch videos, you need to take photographs, and you need to take video, and we need to do all those things possible using a mobile phone. But still at the evening 6 or 7, if we have a mobile phone with 70 or 80% batteries remaining, that is a great thing, is it? Instead of if you fully charge the mobile in the morning, and by 12 o'clock if the battery is empty, means that is not a good battery system. So our aim is to make better batteries, high capacity batteries, and that can sustain long time with a very good capacity or very good storage facility. So I told you The positive is the cathode and negative is the anode, and the lithium is shuttled in between the cathode and anode. And you can see this is a typical battery pack in our mobile phones, and we can see the battery pack, and it contains the cathode and anode and the semi-permeable membrane, and the electrons will eventually shuttle in between cathode and anode. And the most general case, we use the graphite anode, and its capacity is very, very low. It provides only 372 milliamps hour per gram, that much capacity. If you think that number, that is very low, and that unit is nothing but the amount of electrons or charge can store per gram of the material. So we are using the conventional graphite thing, even though in 2020, because it has many advantages, although its capacity is very low. If we compare some of the materials, so people are trying to make very good anode materials for the high capacity or to store more number of lithium or high performance lithium-ion batteries. But the problem is that each and every material has its own pros and cons. If you see the silicon, for example, it has a very good capacity, almost 10 times as compared to the graphite in the silicon case, the second row. But you see the volume change, it is 320%. So I told you the lithium continuously shuttle between the cathode and anode, and the lithium will go and sit into the anode. During that process, if we use this kind of graphite kind of layered material, there is a kind of volume or expansion or compression will happen during the passage of these lithium ions. So which eventually leads to the breakage of the entire battery material. Okay, so this volume expansion is a major issue with the silicon based things, although it provides very good capacity. The same in the case of aluminum, it has almost 640% of volume expansion. But all these materials are actually showing different volume expansion issue, although they are having high capacity. So far, the graphite is the commercially available best anode material, and we are still using that. So our aim is to search for better anode materials. So what is that better meaning? So the better materials are always important. So in practice, I told you, we tend to use the same fundamental material for decades. In 1990s, the Sony first commercialized the batteries, and till now, we are using the graphite as the basic anode material for most of the lithium-ion batteries. So in order to, what is the problem of these things? The problem with the traditional material discovery, it is because of a lot of unsuccessful experiments. You know that while doing experiment, we need to take care of many things. One is the laboratory facility. The material should not be too much hazardous, right? And we need to have a laboratory facility. We need to buy materials, and those materials are not that much cheap. Sometimes the materials are very costly, and we need to have very expensive experimental facilities to test all those things. So there are many things, and even though we have all those things, sometimes the experiment may fail. So there are a lot of investment, not only the human investment, but also many investment, even economically, that is not a very fruitful way. So what is an alternative solution is that the United States White House, the President's House of the United States, they directly involved, and they developed a new initiative. It is called the Materials Genome Initiative, to discover, develop, manufacture, and deploy advanced materials at least twice as fast as possible today at a fraction of the cost. So the United States White House directly involved in this matter, and they invested huge amount of money for the development of materials through an innovative approach, and which can be used for the human welfare, clean energy, next generation workforce, and national security. And the fundamental idea of these materials genome initiative is nothing but the simulations and supercomputers, as well as digital data and data mining. You might have heard about the machine learning approaches and deep learning techniques. So these are all, and the most of the funds of this particular initiative is for to find out better materials for the better future. It is not only the clean energy materials. We need materials for every sector, like human welfare, national security, and most medicine, and all our health system, all those things. So, and I was fortunate enough to work on these clean energy materials even after it was started before my birth. So we need to have a materials, but our main task is to not only to design, but also to design and improve the existing materials. Okay, so now I have a question. So have you heard about the 4 minute a mile? Have you heard about this before? Okay, I will explain what is this mean. So for many years, it was believed that the human body was incapable of running a mile under 4 minutes. And in 1954, that barrier was broken by a doctor at Oxford University. And later, in Australia's John Lanty did it. So this 4 minute mile is a commonplace, like it's a kind of running. So why this 4 minute mile is important here? So I just want to tell you that the two-dimensional materials are one of the vibrant fields of research in nowadays. So the two-dimensional material is nothing but a material which can stay as it is, like in a freestanding manner, and it has a specific length and breadth, but the thickness is a 1 atom thickness. So for many years, it was thought that based on the thermodynamics, the two-dimensional material was impossible to exist. But after the discovery of graphene in 2004, the scientists realized that the two-dimensional material can exist in the world a freestanding manner, and that can provide enormous applications in almost every field. And because of that, the groundbreaking discovery of the two-dimensional material graphene, Professor Andre Geim and his student awarded the Nobel Prize in Physics in 2010. So even after the 60 years after the first report on freestanding graphene and 10 years after the award of Nobel Prize in Physics, the worldwide interest of graphene is still remaining due to its multifunctionality and extraordinary characteristics. So this is, I will quickly go through what is graphene. So graphene is nothing but this is a single sheet of graphite. So I showed you what is graphite. So the graphene is a single sheet of graphite, and we can experimentally achieve that a single atomic thick material. And this is the fundamental building block of all carbonaceous material, because we can roll it make it as a nanotube, we can stack it and we can make it as a graphite, and we can roll it and we can make it as a zero-dimensional fullerene. So graphene is very important. And why I want to mention graphene is here, my research is basically on two-dimensional materials for energy applications and gas sensing. Like I usually design materials to capture toxic gases like atmosphere containing gases, mainly the gases from nitrogen containing gases and oxygen containing toxic gases. So my main research is based on two-dimensional materials. So I just want to mention you the two-dimensional materials. So inspired by the discovery of graphene, there are a large number of two-dimensional materials are recently proposed. Most of them are computationally proposed, like what I do, and the success is that even after the successful our computational prediction, most of the materials are experimentally achieved. That is a great advantage or success of our computational approaches. So as a material design towards clean energy materials, I designed the different carbon containing and non-carbonaceous materials for battery anode applications. And the the top row, you can see all those things are related to the carbon containing materials, different materials. We are trying to achieve a high capacity anode material. And the bottom are non-carbonaceous material. These are different compounds. And I will briefly explain the last one, the one with the red square. It is the boron carbon monolayer, which is actually an experimentally achieved one. So you can see the two cases. The first one is the pristine case, and the second one is called a Stone-Wales defect. So in this case, you can see here all are hexagonal rings, and here I actually made a defect. This is called a Stone-Wales defect. So here in the left side figure, if you remove one atom, you can get a vacancy. But here, the number of atoms are remaining same, but there is a vacancy. It is called so there is a defect called a topological defect is there. So you can see I marked here as 1 to 16 in each place. So if I want to accommodate lithium in both the case, we can have a total of 32 lithium atoms, right? We can have a total of 32 lithium atoms, and if we can calculate the capacity, then it will go a large quantity. But that is not true. The capacity of these two, although it can accommodate 32 atoms theoretically, the capacity is different. Why? Because you can see here, it cannot accommodate 32 lithium atoms. It can accommodate only 18 lithium atoms. If you see, the violet and pink color represent the top and bottom side of the sheet where I accommodate lithium atom. After accommodating a certain number of lithium, eventually the lithium repulsion will happen, okay, and which will not be energetically stable or favorable. So maximum I can accommodate a lithium of 18 lithium atoms, and which is provided a capacity of around 1200, and which is almost 3 times higher than that of graphite. But that is also not suffice in my opinion. So we need a high capacity material. So what these things, all these things provide a large number of data. I told you data is very important. So we need to process the data. We need to store the data. So data analysis and data manipulation, data processing is very important. Another thing I told, the diffusion barrier. So what is the diffusion barrier? So you can see here in this figure, this is a carbon containing allotrope I designed for battery. And you can see, you can see the movie, like the lithium is moving, right? The lithium is moving from 5 to 7, 5 to 6, 6 to 7, 7 to 5. You can see the ring numbers 5, 6, 7, 5, right? So this is moving. And I told you before the volume expansion, you can see here, while lithium is moving, it will the electrode or the anode material is kind of expanding and compressing. And this compression is comparably very low. This compression is comparably very low, and this is an acceptable range. And we know that the lithium will prefer to move in this path, and we can calculate an energy barrier. So how much energy is needed to move lithium from one position to another? So we know that the graphite or any anode material, the layered material, like the lithium from the cathode will move and accommodate in the anode material, and it always try to occupy the most stable position. So each material having different stable position. So we are computationally trying to find out the diffusion. It is called a diffusion. So this is possible only using computational approaches. We cannot use this for the real experimental approaches. So we can suggest to the experimental people, this computation gives us the most stable position and energy barrier like this. And this material is showing this much capacity. So what do you think? So is a good candidate for an anode material? If so, let's try to make it or synthesize experimentally. So we are actually trying our insight. We are trying to give or up insight to the experimental people to make it a realistic thing. So the research is a kind of amalgamation of theory, experimental, and computational approaches. So this energy barrier is actually a little high. So we are actually trying to make a low energy barrier, high capacity material for better battery applications. Okay. Now, if we go to our day-to-day life, like the dreaded. For example, you might have experienced all these things in your life, right? My battery is not working. So why it is happening so? The first thing is that why has the battery performance in my decreased in old phone? So there are a couple of reasons. The first one is, of course, the first one is that the new phone, new facility, new technology. Okay. The second thing is that the loss of lithium due to the reaction of electrolyte with the active material. So there is a formation of solid electrolyte interface in the which eventually loss of lithium to move back and forth. When lithium moves back and forth from the cathode and anode, it moves through the electrolyte and it will form a solid electrode interface. So that actually restricts the more number of lithium to come back to the anode material. It is something like you just take a piece of iron and keep it on the atmosphere. Eventually, you can see that the rust will form on the top of that, right? But of course, rust will be there, but it will not affect drastically the other parts of the iron. Like that, the solid electrolyte interface formation is good, but eventually it will not. It will definitely make a capacity fade or loss, but it ultimately is good for the anode material. So that is one of the reasons for the decrease of battery performance in terms of capacity, battery performance. And the other one is that the new phone and old phone difference. The new phone is much better than the old phone because we use a better battery. Of course, the new technology is always advancing and we have a better battery in that system. And can we put a better battery? Okay, there is a problem. Each battery has its own battery management system, and that is very sophisticated. Okay, so each battery, even though it looks same, the battery management system is very, very important. Even though these batteries and specifications are the same, not all batteries are equal. So that we are the people are suggesting you have to buy a battery. If you want to replace the battery of your phone, you have to buy a battery from the reliable source like a company battery, and you have to put it, because otherwise it may create some problem like exploration. Something will happen upon charging, because different battery and the different handset have its own battery management system and the associated properties. So these are all some of the things associated with the our mobile phone things. And I have a couple of slides and I will stop after that. So I will just want to move to the electric vehicles battery. So that is our ultimate aim. So you can see the Nissan, Chevrolet, Tesla, and BMW, all these companies are using the batteries. But the problem is that still, I told you Tesla is doing its best things, but it costs very high price. For example, the Hyundai Kona is released its electric car in India, and I assume its starting price is around 25 to 35 lakhs, and we can buy a Swift, a Maruti Swift, or the same Hyundai car within 6 to 7 lakhs. So the problem is main cost is nothing but its battery charge. So these all having its own different battery technologies, and this is a typical battery system. And you can see there are many different packs of battery. So if you have assume an LED system, and if one LED, if it gone, I mean if it will damage, so it will not affect the other systems, right? The other LED bulbs will glow as it is. So the same way, we have a large number of batteries, and all small batteries are packed in a different array. So this is a typical Tesla battery arrangement. But the problem is that still we are lacking the capacity issue. So if we can get a high capacity battery, then what will happen? So we can actually reduce the cost, and which can be accessible for each and every citizen of the world. So that is the ultimate goal of the car manufacturers and the scientists to achieve a carbon emission free or fossil fuel free emission world. So we are almost reached the clean energy technologies. So I assume the Jeep and other motors, so this is not an advertisement, this is my personal favorite car, so I always behind that. So I assume these motors will eventually install its electric vehicles by 2020, full-fledged electric vehicles in the United States as well as in India and other parts of the world. Okay, then what is the future? I told you we have a very good set of examples like experimental approaches and a theoretical approach in 1800s, and still we are learning. In the first year BSc or as well as the engineering classes, we are learning quantum mechanics. That is around 100 years back. The theory is developed and we are learning that. So, and we are using those fundamental things to make the things, making new technologies, new development and other kind of things. And now we are in the third paradigm, like computational sciences and simulations, like density functional theory, what I currently do. And the other shift is something like the artificial intelligence and data mining and statistical learning, deep learning. So this is the future of research in terms of computational perspective. So we need to have data. I told you we have data. We need to have the machine learning or deep learning, data mining techniques. And we need to have theory and we need to have simulations, and these can be used for the very fruitfully. We can use it for the potential applications, and of course we need the experimental verification of these things for the real-time achievement of this application. Experimental verification is needed. So we have a lot of different approaches. We have to have machine learning based things to get the proper materials. We are actually, machine learning is something like we are teaching them, we are developing some algorithms and we are teaching our machine or algorithms to generate the desired property of the materials. So this is actually the future of our technology. So the conclusion is nothing but, I know that the prediction is very difficult, especially it is about the future. We don't know what is going to happen next day because the whole year is almost gone because of the COVID pandemic. We don't know what is happening the very next day. But as a science student or a researcher or a teacher, we should think that if you think that the developing technologies to meet the needs of today, we will outdate it soon. So the technologies must be capable of meeting the demands of the future. So this is the takeaway of today's webinar. By saying this, I am concluding my talk, and thank you so much for your kind attention. And if you need some clarification and if you have any queries, I am happy to answer all those things.
So thank you so much, sir. That was very informative and educational. So just like he said, if you have any queries and doubts, feel free to ask him, clear your doubts. Meanwhile, the rest of you can fill the feedback form that will be shared in the chat box.
If there is any query, please feel free to ask. I hope you don't have any doubts regarding the presentation.
Any doubts for anybody? Okay, so since we are concluding, I would like to call upon Ms. Kavya Sunal for the vote of thanks.
Thank you, Olivia. First of all, I would like to thank our resource person of the day, Dr. C.B. Thomas sir, for making this webinar session very interesting and meaningful. I would like to thank Jodi management, principal and our HOD staff members for all the moral support and guidance. We are also grateful to the coordinators of the webinar session, Ms. Needu Rose Thomas and Ms. Sindhu S. for making this a grand success. Finally, the wonderful participants who have turned up from various places for the section. Thank you so much for your cooperation. Once again, thank you to all.
Thank you so much, Sibisa, for accepting our invitation and for the wonderful session.
Thank you so much, ma'am, for the opportunity.
Thank you, participants. Please fill the feedback form. It is provided in the chat box. Feedback link is provided in the chat box. Participants, please fill the feedback form. And thank you for attending the webinar session.